This video is on spontaneous processes, non-spontaneous processes, and our first look at delta G, which is Gibbs free energy. Okay, so the first topic in this video is the first law of thermodynamics, which we have covered. We have just not referred to it as that. And so the first law of thermodynamics is technically states that energy, oops, my eraser is on, that energy is conserved. Another way to say this is the law of conservation of energy. So very similar to the law of conservation of mass, which we learned very early in chemistry, that says mass cannot be created or destroyed, it can only change form. And the same thing is true for energy. We know that energy can't truly be created and it can't be destroyed, it just changes form. And we have talked about this, and the best example of talking about this is in thermochem, which brings about the discussion of if the system loses energy, then the surroundings have to gain it. And so that in and of itself is the first law of thermodynamics. So this idea that Q, or heat of the system, is equal to negative Q of the surroundings is a perfect discussion of the first law of of the first law of thermodynamics, or the law of conservation of energy, because what one is losing, the other one is gaining. And we have laid that groundwork in the study of thermochem. We just have not referred to it as the first law of thermodynamics, but that is what it is. Okay, so that is technically old information, just with a new word attached to it. But what is now new to us is this idea of something being spontaneous. So you might have an idea in your head of what spontaneous means to you in your everyday life. Like if you were to refer to somebody as being spontaneous, like you probably have an idea of what that person is like. But we're now applying the idea of being spontaneous or spontaneity to a reaction or to a process. And so a spontaneous process is one that proceeds on its own without any outside assistance. It's important to note a couple things, that spontaneous reactions or processes occur only in one direction. So meaning if a process is spontaneous in the direction that we're speaking of, then it would be non-spontaneous in the reverse, and we'll see an example of that. Okay, so here's a non-chemical example just to paint a picture in your head. So if I was holding an egg in my hand and I dropped it onto the floor, it is absolutely going to break. There's really no question asked that egg is going to break when it hits the floor. So that process is spontaneous, meaning it's occurring all on its own. Now, yes, I dropped the egg, but once the egg has been dropped, there's no outside assistance that's helping that egg to break. It's just going to break. Okay, it's kind of like a natural thing that happens. You might say gravity is assisting, but that's a different story. Okay, and think about this also, what we just said about the reverse process being non-spontaneous. Well, if dropping an egg is spontaneous, the reverse process would be that egg being broken and turning around and creating a unbroken egg, right? And you're laughing because that doesn't make any sense at all. And thus that process is non-spontaneous, right? That's never going to occur, even with some kind of outside assistance, right? More of a chemistry example is gas expanding to fill a container. Like a balloon, right? If you put gas into a balloon, the balloon just gets bigger, right? It fills up because the gas is expanding to fill that container. It just happens. It's a spontaneous process, okay? So one thing that we have to discuss is that sometimes the spontaneity of a reaction can be different depending on the pressure and the temperature. We're actually really going to focus on the temperature, but pressure can actually affect it too. So let's make a note. I'm going to say must consider temp and pressure in regards to this idea of whether a process is spontaneous. And I'll give you an example that hopefully will make sense to you. Okay, so here's my example. If I had H2O in the solid form, so ice, sitting on a lab table or a desk at 20 degrees Celsius, and that's fairly close to room temperature. It might be a little bit below room temperature, maybe 65 degrees Fahrenheit or something like that. But the question here is, would that ice cube melt spontaneously at a temperature of 20 degrees Celsius, right? Room temperature. And I surely hope that you're saying, yes, it's just going to melt. So H2O melting at 20 degrees Celsius is a spontaneous process. And then here we go. So we can intertwine a lot of ideas here, which means that H2O melting at 20 degrees Celsius is spontaneous, but H2O freezing at 20 degrees Celsius would be non-spontaneous. And you should be saying, yeah, that makes perfect sense, because water on my desk isn't going to freeze at 20 degrees Celsius. It's not going to happen. That's a non-spontaneous process. Okay, so that would be the reverse of that reaction. However, if I change temperature, we can change the spontaneity of this process. Think about it. Let's now say I have H2O melting on my desk, and the room is extremely cold, and it's -5 degrees Celsius. Will the ice cube melt? Right, well, think about it. 0 degrees Celsius is your melting point or your freezing point. So if it's below that ice cube's not going to melt. It's not going to happen. So because I have manipulated the temperature, we've talked about H2O melting. Well, guess what? Sometimes H2O melting is spontaneous above the melting point, and sometimes it's non-spontaneous below the melting point. It's just not going to happen. So this second example is non-spontaneous. And that's because, we have had a manipulation of the temperature. Okay, and that goes back to the fact that we must consider temperature and also pressure sometimes to decide if a reaction or a process is spontaneous or not. Pressure more so comes into play. Like, where would pressure come into play? I think when you were talking about, do you remember these? Like phase diagrams, solid, liquid, gas, right? Pressure could come into play there, where we did talk about like the triple point and raising the pressure and all of that stuff, that you could see a question maybe creep in, like, does this thing melt spontaneously at this pressure, yes or no? You'd probably need a phase diagram to answer that question. So pressure can also influence the spontaneity of a process, but the easier one for us to think about is temperature. So I just want you to keep that in the back of your mind, that just because something is spontaneous at one temperature, like ice melting, doesn't mean that it's spontaneous at all temperatures. Okay, so something really important kind of to think about. All right, there's a couple of practice problems on your paper. I summarized them very quickly here, but if you want to pause this and try to predict if the reaction is spontaneous, non-spontaneous, or in equilibrium, you can. Otherwise, I'll just jump into it. So A really says on your paper, when a piece of metal heated to 150 degrees Celsius is added to water, at 40 degrees Celsius, the water gets hotter. Right? Well, is that going to occur? And the answer is yes, right? If you put a hot piece of metal into cooler water, the water gets hot. It's just gonna happen. So that is spontaneous. It's spontaneous in the forward direction, right? Meaning the reverse reaction, which would be what? The water the cold water giving heat to the hot metal. That doesn't make any sense. Heat always flows from hot to cold. So of course the metal is going to give up its heat to the colder water. So it would be spontaneous in the forward, but non-spontaneous in the reverse. B says water at room temperature decomposes into H2 and O2. Well, step back and think about this. That would mean that your cup of water sitting on your desk would naturally break down into hydrogen and oxygen gas at room temperature. And that does not occur. So this H2O decomposing into H2 and O2 would be non-spontaneous in the forward direction. However, in the reverse direction, it would be spontaneous. And you might say, no, it's not. Yeah, actually it is. If you take H2 and O2 and put them together, they do need a source of ignition. They need a spark. They will create water. So that actually is a spontaneous reaction in the reverse. But in the forward, it's non-spontaneous. And then C says benzene vapor, C6H6, at a pressure of 1 atm condenses to liquid benzene at the normal boiling point, which is 80.1 degrees Celsius. So you might be tricked by this initially, but we're talking about condensing at the boiling point, which means that in addition to condensation happening, we have evaporation also occurring, and this process is in equilibrium. So that's this, right? What we just got done talking about. Okay, one last thing to wrap up this discussion. Is spontaneous and non-spontaneous reactions or processes, and then something called delta G, or Gibbs free energy. So delta G is something we refer to as Gibbs free energy, or sometimes just free energy. And we'll get into a discussion of delta G later, but for now, this is just your intro. We're just going to learn that the sign of delta G tells us info on the spontaneity of a reaction or a process. And delta G can actually be three things. It can be positive, it can be negative, or it can be equal to 0. And this is all we're going to take away from today. If delta G is 0, then the reaction is at equilibrium. Okay, it's just what it is. And again, don't be too concerned that you're like, I don't know how to calculate delta G. That's a later discussion. Okay, right now, all we're talking about is that delta G, Gibbs free energy, and what its sign is, or if it's 0, it tells us information on spontaneity of a reaction. So if it's 0, the reaction's at equilibrium. If it's positive, the reaction or the process is non-spontaneous. And then, as you might guess, if it's negative, the reaction or the process is spontaneous. And that is all you need to know at this point in time for delta G. Okay, so we could kind of go back up to our, maybe we will, go back up to this discussion where we were talking about temperature. And so what now we can say is, in this first example of H2O melting at 20 degrees Celsius, we know that that process is spontaneous. That would give us a delta G value that's negative or less than 0. H2O melting at -5, we said doesn't happen. It's non-spontaneous. So that would give us a delta G that's positive or greater than 0. And then I wonder if you could tell me where delta G would be 0. And I hope you could. And that would be H2O melting at exactly 0 degrees Celsius. Because when you have melting at at the melting point, you're in an equilibrium situation. And so if you're in an equilibrium situation, you have both forward and reverse processes occurring at the same time, and delta G would be 0. So for now, all you need to know is the difference between spontaneous and non-spontaneous processes and what value of delta G goes with each of those processes.